All right. Good afternoon, ladies and gentlemen. Thank you so much for joining us today to make this session possible. We saw early interest in terms of how many people are coming in, and I'm excited to have so many people here. Hopefully, all of you love Surface. So thank you for the opportunity here. As a program management leader at Microsoft, I had an opportunity to work on Surface Pro 3 and lead and represent a group of people who are super passionate about technology. They are taking technology to the next level every day, innovating every day, and making sure we have great products and making Surface the most productive device on the planet. But more importantly, I'm excited here because of you. You are the people who are taking those technologies to people, touching them in their real lives and making a difference in the lives of people. So on behalf of Microsoft and our team here, thank you. Please join me in a round of applause for yourself. 'Just to give you some context, 2 days back, Cyril talked about the business side of Surface. Yesterday, Brett Muzzy and his team talked about the software side of Surface. This morning, Ralph talked about the design side of Surface. I'm going to talk about the hardware side of Surface. How do we take the design vision we had in terms of what we want to go make Surface and what engineering went behind it to make that possible? That's the story today. And tomorrow, our team is going to talk to you about the support that we provide on Surface. So that kind of covers the gamut of activities we do on Surface. Hope you'll find it exciting. This is supposed to be a 300-level session. I'll go into deep engineering as much you show interest. Well, let me tell you that there's a lot of swag that I want to give away. I don't want to go back with anything to Redmond. The best one I have is the Surface Pro 3. In between, I'll have some quizzes. We'll give away a whole bunch of stuff. But I want to see the energy and the love for Surface. Okay? Awesome. How many of you have a Surface Pro? Surface device. Fantastic. We love you. We love you for thinking that we are worth it. My job here is to tell you that we are taking every care, going into every little detail to make that product worth your money. So thank you. I'm basically here to talk about a few stories. It's about 9.5, 10 months of effort this team has gone through. Of course, there is a team that works on long-term innovation. Some of that innovation rolls into our products. But the execution team that takes this product and says, OK, let's go ship a product in the next 9 months, that's the journey I'm going to take you through. It's very difficult to pack those 9 months into 1 hour. So I'm going to tell you some of the most interesting stories or decision factors that we had to go through. It shows you the engineering challenges, what the team had to go through, and what are the trade-offs, and how do we put customer first all the time. Before we go there, I want to talk about design vision. Our vision for Surface is to make Surface the most productive planet on the earth. With Windows, we have a great presence on the desktop world today, but our goal is to make sure that with Surface, we change that, we provide even more productivity. If you look at the history of productivity, I'm sure everybody knows about this. Thousands of years back, people had to walk from one city to the other to deliver a message. Then we had carts, and then you had pigeons delivering message, and then you have Gutenberg's printing press, and internet changed everything. So in this era, to increase the level of productivity requires a complete paradigm shift in terms of how we think about things. So our vision is to make sure we take Surface on that journey every day. So you will see new products from us every time. We are committed to the hardware business, and that's something we'll stay true for a long time. These are the stories I'm going to talk about. How did we make it thinner? So how many of you attended Ralph's session this morning? Great. A few of you. So you might get some prize because you may be able to answer a question. So our vision when we started with Surface was how do we make laptop and your secondary device into one device by increasing productivity. Let me give you an example. A lot of times I fly a lot for Microsoft to suppliers, partners, customers, and most of the time when the airplane is landing, people have their laptops on, they're working on it, and the crew announces that, hey, this is time to shut down your laptops. It's time, you can continue working on your small devices or tablets, but put them in airplane mode. And I can see people, including me at that time, would shut my laptop, put it away, put out your iPad or your other Windows device, and then put it in airplane mode and start working. with Surface Pro 3, those of you who travel, and if you see Surface Pro 3, you see that's a big change. That's one scenario I'm talking about. I just unplug my keyboard, put it aside, put it in airplane mode, and continue to work. So we are trying to reduce the shifting cost of moving from one device to the other, moving your applications and everything, make it seamless. But in that journey, so we launched Surface Pro 2. Many of you would have seen it. As Ralph mentioned, it looks like a tank. It's robust. It feels like you can hit somebody with it and nothing will happen. Sorry, I'm HR violation. But our next step was, okay, how do we heard great feedback. We had absolutely great feedback from customers like you that, hey, we love the device. We're able to use this for advanced applications, graphic software, stuff we can run. But still, the uptake was slow. And one of the things that we found was, how do we make the screen size larger? We wanted to make the screen size larger. We wanted to make it thinner, lighter, and affordable to the extent possible. But one thing we wanted to make sure was that it was the best-in-class design. So we never cut cost in any area. We wanted to make sure that's the best-in-class design. So as a part of that, these are the stories I want to tell you. How do we make it thinner and lighter? The continuous hinge that you see, I have samples of here. I'll show you some close-ups. Material and finish, how do we think about them? Keyboard, pen, and reliability issues that we faced. We talked about Surface Vision. I won't go through this. This is a busy slide. This is just a flash. All this information is available on the web, so I don't want to waste your time. But this is just a flash. All the innovation that went into making Surface Pro 3. And there is a team of people who worked on this day in and day out for 9 months. And the first picture that I showed you is so special for me. This one. This is no fancy picture. Very personal for me. This is my hotel room in a place I cannot disclose where it is, somewhere in the world. This is the first ever Surface Pro 3 assembled with the real parts. Group of people, Andrew Hill, who is my partner in crime. He was supposed to be on stage. He's expecting a baby, so he couldn't make it. He and I and a group of people gathered together in my room, got all the parts, assembled it, and said, hey, is it beautiful? Is it worth shipping? This was a moment in time when we said, yes, we are ready with it. And after that starts the real journey of making, how do we make this scalable? How do we make millions of pieces? Can you find anything interesting in my hotel room? Chopsticks, yes. This is something we love to talk about. Surface Pro 3 was designed with Surface Pro 2. Our engineers use Pro Engineer, 3D software, Maya, Rhino, all kinds of heavy graphic-heavy software on Surface Pro 2, and today they use in Surface Pro 3 to design our next generation products. So that's what we want to make sure our products are capable of. As I tell you those stories, something to keep in mind is there are 4 things that are important. For a program manager like me, there are 4 elements that come into play on every decision, which is how do we make the performance best? How do we increase the quality bar so high the customers are going to just love it? Which is where the customer focus comes in. And we've always put customer first in every decision that you will see as we hear the stories. The second is schedule. Can we make it time to market? There are competitive pressures. There are pressures within the team. There is a commitment to the business. We want to make sure we can ship in time. So whatever innovation we are doing, whatever changes that are happening in the engineering trade-offs, we are constantly thinking, oh, can we ship in time? Do we take the risk or not? How do we think about it? And there are frameworks, but frameworks are worth whatever value it is. But there is passion in the team to drive to closure. And then there's cost effectiveness. Shareholders, we are a new business in Microsoft, doing fairly well right now, but there is always pressure from how do we make sure the costs are contained in a reasonable limit so that we can go back to shareholders and say we are creating value. And finally, we talked about great prototyping facility we have in Redmond, which can create any part. We think about an idea. The next day, we are looking at the parts on the table. It's just unimaginable. But how do we take that idea and then make sure we can make millions of these pieces, whether in China or elsewhere around the world? How do we find the suppliers who can make it? How do we make manufacturability a possibility? So those are the 4 trade-offs that happen. And then it's like solving a Lego puzzle. But for me, it's like solving a Lego puzzle when you've assembled 2 pieces and you find that the other pieces are changing their size and shape. It's like that. So this is just to kind of give you perspective on the stories that you see are all happening in parallel. and they're all having trade-offs against each other, which are impacting the others. So my first story is around enclosure and layout. Some of you who've seen Ralph's session probably saw the enclosure, but I'll give you a little more detail on that one. So when we decided to make Surface Pro 3 thinner, we had to sit down across the team and say, what are the different layers? There is the touch and glass layer on the top. There is the enclosure. There is components inside. There is a thermal module. There are screws inside. There is battery inside. Those are the kind of high-level big components. And then we looked at the stack up and said, hey, okay, we can make this one thinner, but how do we make the battery thinner? If you make the battery thinner, what happens to battery life? There is a trade-off there. And then the tallest component after all the optimization we did was the thermal module. So we had to go invent a completely new thermal module. We talk about that and the engineering behind it. So in the stack up, we decided to work on this is how the bucket looks. We call it the bucket. This is how the case looks. I didn't say that, but this is how the case looks. This is from one of the early prototypes, so don't go by the looks on this one. We were trying to experiment with how do we make it. So at that time, in Surface Pro 3, we had invested millions of dollars on magnesium molding. So there is a process by which we injection mold magnesium to make Surface Pro 2. That's how it was made. And then after the injection molding, you send it through a CNC machine and polish them, make it beautiful. Then we had a PVD process, physical vapor deposition process, to give you that black finish, really beautiful on Surface Pro 2. But what the biggest challenge was with the time frame that we had in this project, it was difficult for us to use magnesium molding for two reasons. One is magnesium molding requires tooling. Just like any plastic molding, it requires a tool into which you inject liquid metal. But the lead time for tools are like 6 weeks, 8 weeks long. So once you finalize a design, it's a snapshot in time. Once you release the tool, you have to wait for 6 weeks to see the output. So we said that is going to be a killer process. There is no way we can use that with the kind of changes we are expecting across these Lego blocks happening on a dynamic basis. The second thing was the molding machines we had invested in were not sufficient to mold a large piece like this. It had to go to the extreme end, which means our yield losses would be high. So we had to think about a new model. And then our mechanical engineering team came back and said, why don't we just take a piece of metal and just shave off the material through CNC process? And that's what we finally did. When you do that, there are several things that come into mind. One is, what material do we pick? Magnesium versus aluminum is the highest order decision that comes. If somebody knows about materials, magnesium is about 30% lighter than aluminum for the same volume. So we wanted to make sure though it was expensive, difficult to manufacture, not many suppliers. If you look at Apple or other devices, a lot of people are using aluminum, and that is a kind of mature industry. But we said we want to make it lighter. By going to magnesium, we were able to make it lighter by 40 grams, just on the case alone. And then once you pick magnesium, then we had choice between AZ31B, ZK60, AZ80. These are all kind of variants of magnesium. Which one do we pick? So there is, in the prototyping lab, we built a few. We had a few suppliers build a few. And within a period of like 2 weeks, we got samples of all these different materials. And then you kind of drop them and test them. How does it happen? What happens to the vent holes? What happened to the details inside? Do the bosses break? What's the strength? Of course, there is material strength information available in the engineering databases, but unless you build a piece, you don't see what is real. So we build those pieces, test them, and finally we decided to take AZ31B. Once we picked the material, we had to go find who's going to make this now. We have the sample, like we can tell somebody this is the design. It was all designed in Redmond, but we had to go find a supplier. So Andrew took off on a flight to China. In like 24 hours, Andrew took off to China. I took off to Malaysia. We were meeting with suppliers in the next 48 hours, meeting with people and finding out who can make this. And from our database, we have pulled companies who had the most advanced kind of CNC facilities. We met them, looked at the facilities, and then finally we selected somebody, shortlisted a few people, and then most of the people used oil. So there is a coolant that's required. Magnesium is highly inflammable, so we have to control the temperature inside. We have to have a good cooling process to make the CNC process. When you hog out so much metal, there is a lot of heat that's generated. We said, we don't want to use oil. We want to use water. And they were like, are you crazy? Like, it cannot be done. We said, it's a requirement. We want you to figure out how to make, like, shift from oil. So for the first build, we said, okay, we will let you make a few with oil. Yeah, so because oil is not environment friendly. So we wanted to make sure when we make a product, it is absolutely environment friendly all the way from cradle to grave. So that is one of the choices we made. The other choices we made was complete removal of nickel from the paint so that there is no ledge. When your kids put it in your mouth, it is safe. So safety and environmental considerations were core to some of the decisions that we made. So that's why water. Good question. So then we had to literally re-lay out some of the manufacturing facilities in the plant to make it ready for water. So that's the level of detail that we've gone through. I will do a quick close-up of this one for those of you not seen to the level of detail that we need to do on this one. This is the magnet. So when you see your kickstand close, you can see that at about 10 degrees, it kind of pulls in and gives you a sound. I am not exaggerating. We spent about 1.5 months trying to perfect that sound. And people would call us crazy. We would go, Ralph, Andrew, and I would sit down and say, okay, dip. No, it doesn't sound like. And there will be people who would be standing there, these guys are crazy. And then we say, do we use, say, N48 magnet or an N50 magnet? How do we, and then when you make the magnet more powerful, how does it impact the RF inside? Once we decided the paint inside, we said, hey, the radio frequency RF required conductivity inside, so we had to etch these areas to make sure they're conductive inside. So there is so much trade-off that happens as a part of this process and so much learning that we are blessed to have gone through that learning process. So this is the enclosure. Anybody wants to see after the session, you can hold and see. This is one of the early prototypes, as I said. And as a part of that process, we were also seeing not just making it lighter and bigger, but making it thinner. So we had to go and literally make custom screws, because when you reduce the height of the screws inside that is holding the motherboard and components, you want to make sure they're strong enough, robust enough, it doesn't fall off. So we had to develop special threads, make special screws, make them lighter with lighter material to make the entire stack up lighter. Quick glance on this slide, 0.55 millimeters of Gorilla Glass cover. So even for, We made custom Gorilla Glass cover to make sure it is thin and strong on the top. And then cooling fan and optimized layout is something I'll talk about now. So this is the picture. I wanted to bring a picture of Surface Pro 3, but I thought Surface 3 just announced, so I just brought a picture of Surface 3 enclosure. That's how, at least I think it's beautiful inside. The layout that it's done, we sit together with designers, the engineers and designers sit together and say, hey, how do we make these decisions? Where should be the curve be? And it is unimaginable the amount of time we sometimes spend on one of those curves, though it is completely hidden inside. So there is extreme CNC machining that is happening, material selection, machinability, and availability. These are the things we just talked about. Now coming to the stack up, I told you we looked at every level inside the stack up to make it lighter, stronger, and thinner. And this is, if you see, this is the layout for Surface Pro 2. This is for Surface Pro 2. If you can see here, you can see, can you see the lines when I'm drawing? Okay. So this is the thermal module. So this sits right on top of the processor so you can cool. As you can see, there are these vents that is going across. This was huge. And the stack up on this was so tall that that's how we ended up at 13.5 millimeters on Surface Pro 2. So we had to find a way to completely reinvent that and transform that into a smaller size, but at the same time gives us optimal performance. And then once you make the batteries here thinner, this is the initial layout. This is not the final layout. I'll show you the final layout in the next slide. But we said, okay, we'll put the batteries here. We're going to put the thermal module here. We'll make a single thermal module which is as efficient as 2 different fans in Surface Pro 2 and make them thinner. But then that, when you reduce the thickness of the device, then your battery has to spread. For the same amount of power that you need to generate, you have to increase the size of the battery. And when your size of the battery increase, as you can see in the next one, you'll see this kind of started growing because we wanted to make sure that it's kind of 10 hours of battery life, 8 hours of video playback. So this started growing, and the motherboard team came back and said, hey, you're growing the battery. Stop. We don't have any more space to condense the components. So there is an interesting dialogue that happens there. Anyway, so it is very interesting. There is mechanical engineers, there is electrical engineers, RF engineers, and designers all sitting together and saying, okay, you're crazy, and it's fun. But in the end, it's all with great intent. As one of my mentors says, we are all paid to bring our perspectives to the room. Because if you're not passionate about what we're doing in each of our functions, we will not have a great product. So here is the layout. Finally, we work closely with the motherboard team to make sure we can condense these parts. We have an extremely tight SMT process. It's a surface mount process to get these components on the printed circuit board, PCB. One area where, after all this was done, then when we started to put the memory, we had a trouble because the memory was taller than the thermal module. So what do we do now? So we have a patent. We have invented a way to put memory on both sides of the printed circuit board. And it's a really complicated thing to do because you have to have the connection so tight in terms of tolerances. Otherwise, even during a drop or something, it can get damaged. So there is an intense reliability test that went into it to make sure we have great memory in the device as well as completely packed motherboard optimized to the size we can. I want to show this picture again. Just take a look at this. I will connect the dots later. Take a look at this. This is the hinge that you will be seeing shortly in another story. When all this was done, we figured that when these Lego blocks are moving, one of the blocks had moved farther, that we had less space for one of the hinges. So we'll see that when we talk about the hinges. So here is the battery. These are the 2 batteries. We had to make custom batteries. And then we wanted to seal the device completely. And when we seal, I'm sure there is feedback on that. We'll take it to Q&A. But when we do that, we had to make batteries custom. When we make custom batteries, a lot of batteries are kind of serviceable batteries. They have 6 months, 8 months lifetime. But we said, hey, our batteries should last 3.5 to 4 years, and without taking them out or servicing them. And so we had to go work with suppliers to make custom batteries that lasted longer. Here are the magnets that I showed you earlier. These are the ones that give you the beautiful click sound. Yeah. This is just to show you a zoom in of the motherboard itself, how condensedly packed it is. This is how it is. You can see this is your mini DP connector. This is your USB. Some of you asked earlier in one of the sessions, can you throw in one more USB? I'd like to sit down and review this design with you. Yep.
Was the motherboard size part of the reason why it's a micro SD card slot in there instead of a full-size SD card?
So one of the things is we looked at user behavior. There are kind of different trade-offs. One of the things we found was people were taking pictures with the phone. A lot of the data saving that is happening on the micro SD. So that's the reason why we picked micro SD. Yeah. And size, of course, is a additional consideration, but it's a secondary benefit.
When did you start this process? Because Surface One is only a couple of years old.
Yep.
It obviously must have took you a long time. When did you guys actually say, hey, we're working on Surface 3?
Yep. So it is difficult to pinpoint a date, but April of 2013 is when we said, yes, we're going to make it, and by next year, in 9 months, we're going to have this ready with production. That's when we made that decision. But that decision is not usually, it's brewing all over the place, right? There is conversations happening. Okay, we have a roadmap. Right now, we are thinking about what's happening in the next year and the year after. So there is a roadmap, but the real work started around spring of 2013. There is some amount of, for example, there is thinking around what can we do with thermal modules, how can we make them thinner. There is Stevie Batish's team, who's our mad scientist in the team, who thinks about what happens in the next 3 years, what do we do with connectors. So there is a long-term thinking team. There is always brewing new technologies, and then we review it in these teams and say, okay, do we feel confident that we can get this into finally a launchable product?
Was Surface 2 in the market out when you started that?
Yes. Yeah, we designed it on Surface 2. That's your Intel i7 processor here, and here is the thermal module. It looks so beautiful. It looks like a gold chain from India.
Quick question.
Yeah.
How did you model the heat dissipation before you went to fabrication?
Yes, I'll talk about that. Let's go. That's a good segue to the next section. But before that, here's my quiz. How many custom components did we make on Surface Pro 3? Gosh, I have to give you all T-shirts now. Okay. I think I'll spend all time distributing this, so I'll just leave it here. Those of you honestly answered should come and pick it up, please. All right, that's a good segue into your question. How did we do the modeling? So there are two levels what happens. One is we have advanced modeling software for thermal engineering with the mechanical engineers. So we go and kind of build the models on the computer, simulate them, and see how the airflow happens. Just like I talked about the enclosure here. Initially, we do a soft modeling. We say, how do we make it? And then we go to a prototype and make prototype shop and make small samples of those, like 3 or 4 samples, and say how good it is. But a lot of times, the material selection, how much heat dissipation it can do, how the fan, when it rotates, what is the cubic foot per meter airflow that happens. There are a lot of things that need to be studied. It is not always perfect in the prototype. But we do this and say, hey, directionally, does it seem right? Are the decisions we're making taking us in that direction? And then we go make these parts with suppliers, just like we did. I'll talk about that. So let me give you an idea about the fundamental difference between Surface Pro 2 and Surface Pro 3. Surface Pro 2 had the traditional fans. So you have the fans here, 2 fans here. They pull in air from outside at low speed, and they spin the air at high speed and spin it out from here. So if you can see, the red arrows is where the air goes out. But what happens is, if you look at this graph, you can see as the airflow increases, the pressure increases. At a certain point in time, when the velocity becomes so high, your efficiency starts dropping. So we said, hey, why don't we reverse this? So we said, we will do the opposite. Let's pull in high-velocity air, because usually air is cold outside, high-velocity air, and capture it at the closest possible place, because once high-velocity air comes inside, kind of slows down if the fan is too far inside. So we have high-velocity air coming from inside, and then we have low-velocity air spreading out and going all over the place, kind of goes out like that. So this was a completely fundamental shift. So this is one step in terms of how we solve the problem. But still, we haven't solved the problem of height. So we had to literally combine the heat sink, the pipes that go on top, and the fans together. And that's what we saw in the golden chain earlier. Here is what it looks like. So if you see here, this is where your air input comes from. This is the fans that rotate at high speed and then cools the air and sends it out from here. If you see here, this is the thermal model. This gives you an idea about the temperature here, and the blue ones are the colder temperature. So that's how it works. And people like me geek out on what I'm going to show now. That's how the airflow pattern is. Sorry? It is simulation. Yeah, simulation of the final product. It's not simulation of the design. Yeah. This is a quick video of how the fan operates. This was, from a team perspective, this was an equally challenging, just like the enclosure. Same thing. There were two people who were working on this. We said, okay, is it possible? The prototype looks good. The third day from then, one person flies to Taiwan, the other person flies to Japan, find out how do we make this now. And there is kind of relentless pursuit of perfection. People, once you have the idea, there is no barrier to stop them. It's like whatever it takes, we're going to make it happen. So that's what, as a team effort, there is a value of perfection that we kind of try and drive. I know like perfection is out there, but we are always saying that, hey, how do we make it better? How do we make it better? So this is what finally we achieved in terms of size. That's end of story one. How do we get from 13.5 to 9.1? Do you love what you see so far? Yeah. Okay. All right. Next quiz. How many suppliers did it take to get all the parts? I have a mouse. Higher. 200. Who said 200? It's more than 200. But I thought I'll round it off. It's 227. All right, now comes the next fun part, full friction kickstand. When we launched Surface Pro 2, there was a lot of feedback. People said, hey, this is great in terms of kickstand, but I like to keep it on my countertop and use it in a completely open position, or with a higher angle. Students wanted much more shallower. Office workers wanted a different angle. Artists wanted to have it in different angles. So there's we did not have a statistically significant data on what angle should we pick. It is much easier, by the way, to pick detents having stops, because engineering-wise, it's much easier. Continuous full friction is one of the most complicated things on the project, among a few other things, but this is crazy. I'll tell you why. But before we did this, in December, in December, November, end of November 2013, we sat down as a team and said, okay, we have two options. We can go with 3-stop hinge, or we can go with continuous full friction hinge. And we had a couple of ideas on the desk. We had modeled them, but the team said, we are not sure whether we can make it. We don't know what it'll take, but there's so many unknowns with this design. And if you have to launch in May, June timeframe, it's a risk. How do we think about it? So the product leadership team, we sat together and said, okay, what do we want to do? We can launch something that is easy and say, okay, we launched something, or we can say that, hey, we stretch the limits of possibility, and we are going to try this. So there were kind of two choices, and we said, we're going to try this one. And then there were people, finance and other people said, hey, you're taking a big risk. Do you want to have a team of people who are constantly, in parallel, working on the 3D hinge? We said, no. We're going to have bet on the future. We are not going to have somebody work on that separately for this one. Because it kind of takes away the focus from the team. If you don't have a backup option, it's not a good feeling. But it also drives you to the ultimate possibility of making it happen. So that's what we did. We said we're going to bet on the future, extreme focus on the team, and customer-centric approach. So when we build our first prototypes, I told the team that, hey, one of the most difficult places that people sit in are airplane seats. In economy class airplane seats, people are sitting and working, and it falls off, or it doesn't have the right angle. And if we are able to solve that, that would be a great thing. So somebody on my team kind of joked me. It's like, so are you saying we have to fly every time we have to test a prototype? So it was a funny remark, but it was serious. So I have a friend who's a technical fellow in Boeing. So I called him and said, hey, dude, can you ship me 6 seats? And he was like, what are you doing with seats? Why didn't you go fly? But anyway, so he helped me ship 6 seats to my office. And every time we build a prototype, me or somebody on my team, we would go sit on that and say, hey, how is it feeling? Is the center of gravity in the right place in terms of different heights of people and thigh length and everything? So this was something that I feel passionate about, that we are focused on the customer. Is it perfect? No, we have to work harder, but at least we are constantly thinking about what are the challenges our customers are going through and how do we solve them. You can see these seats, they're sitting in the booth if you've not been to the Surface booth. And a lot of my colleagues still, when it's in my office, it's just a joke. People put Post-its on this saying, hey, Delta misses you, Delta loves you, all kinds of stuff. So from the 3 or 4 ideas we had, we shortlisted one of the designs. It is a really complicated design. I'll show you in the next slide. But one of the criteria we had was it has to be absolutely beautiful in terms of function. The other thing is it has to last for 3 years. Just like we said, the battery has to last for 3 years. There's no way you can easily repair this. So how do you make sure the friction hinge can last at torque levels, at the desired levels, all the way up to 3 years? And how do you define 3 years? That's an interesting question. Some people never use it. Some people use it every day. Some people use it every hour. So we had to kind of get a distribution pattern of how people use it and model that and say, hey, how do we define our 3 years? That was a tough order because, as you see in the next slide, the design that we had is something that has 8 parts on each hinge. And mind you, this is fitting in the space. I have an exploded view to show you. This is the hinge. And if you open this, you can see. And this was the killer part, the black one. I have it in black for a reason. It was, what's it called, the joke, the black duck, whatever? Black swan. It was the toughest part. Because what it does is there is a cam inside. The shaft is in a cam shape. It's not circle, so that you can get the friction level separately at different points. And then this creates the friction on the cam. So there's an arm that kind of moves around. But what happens is when you want a life of 3 years, when it moves nonstop, this is metal contacting metal. So there is friction, heat generated, and this guy breaks. So we said, okay, let's do this. Let us go make some grease pockets. So we said, okay, let's put some grease pockets. So we added some grease pockets. And we did that. It is working fine. At about 1.5 year life, it will break because the grease pocket became stress points. As you can see, the megapascals on those are higher. So they started breaking. So we had to experiment so hard on this one. The toughest part was it goes through literally 17, it takes 17 days once you make a change to get something out, because it goes through a long process. Once these are cast parts, then it goes to sintering process, then it goes to pretreatment, then it goes for finishing. By the time it comes back from all over China, it's 17 days. So we had to think ahead and say, okay, what are the things that could go wrong? And we did not know what else could go wrong, but we had like 4 or 5 different options. At the end of 17 days, then you go see, okay, which is the one that works long enough. And then finally we found one option, but when we got a lot of 15 or 20 pieces made, a batch of 15 or 20 pieces made, they had kind of different levels of performance. And we said, hey, how do we solve this? Like, we couldn't understand what's happening. So one of our engineers actually traveled with the hinge, with the component, like everywhere. And we found that there is a location somewhere in China, I can't talk about it, but there is a sintering oven where the temperature distribution was uneven. So you would see that the performance of these parts are different for different ones. So we had to work with them for about a week to get the temperature distribution right across sintering ovens. And then we figured that they did not have enough sintering ovens, so we paid money to order more of them. But it's a fun exercise. This is to give you an idea about all the places that this hinge has to travel before it gets made. The map below, about 7 locations across China, 17 days of lead time on that single part. This is the force curve. So in terms of user experience, what we wanted to do was, when we opened the hinge, we wanted to make sure there is a little slot here which makes it easy for you to open the hinge, open the kickstand. But when you open it, we wanted about 10 to 20 degrees of space where it is easy to open. So it gives you a spot, then you can start pushing from there. But most people would not want to keep it straight. So about 25 degrees was the sweet spot where people will start, okay, this is the point at which we start using it. So as you see in this curve, till about 20 degrees, 20, 25 degrees, you can see it goes flat. There is literally no friction. And then we had to steep up the friction. But when you steep up the friction, there is an interesting thing that happens. You push this further. If you keep the same friction level, then because the center of gravity of the device is on the top, at the same friction level, it requires lesser effort for you to push it, right? So when you're writing, you might see it just goes down. If we had it that way, so we had to fix that. So you can see, we wanted to make it easier for people to go from here to here, and then here we had to increase it a little bit, because towards the last mile, you want to make sure there is enough friction or torque in the system so that the device doesn't kind of flat fall. So that's how it is. And when you pull it backwards, this is what happens in the friction level. So all this was done. We were super excited about the hinge. We were getting good parts. And when we went to the assembly line where the device gets assembled, our tolerances of these lines are microns. Like every device has to meet 0.2 microns, 0.3 microns based on what we are looking at. And we wanted it consistent, the gap between the kickstand and the body. So when we did manual assembly, this was not consistent at all. So we had to go make a special CNC machine to assemble this in 3 axes. So there is an arm that picks up the kickstand. There are 2 arms that pick up the hinges, assemble them to the case, and then before it assembles to the kickstand, it goes and measures that what is the offset, and goes CNC machine shapes off material and does a custom fit of this one. That's how we get this. It was several $1 million worth of machinery, but it was worth every penny because it gave us a beautiful device. So that's automation. And that is what it helped us achieve. That's end of story 2. Sorry? Let me flip the question. So there is a reliability spec we usually don't talk about. Let me ask you, how many times would you use it? No. So let's talk after the session. I'd like to know, how many times do you think is realistic? We've done those modeling, and we've done in such a way that it can meet 99 percentile of people using it on a daily basis for 3 years, not including 1 weekend a day, in a week. Sorry? Yeah. Easy. Much more than that. It can last much more than 3 times a day. The only reason we don't talk about it in specific is we don't want phone calls asking why not this number and why not that number. It's just a distraction for the team. But I'm happy to talk to you about this offline. All right. What car do you associate the Surface Pro 3 with? Who said Porsche? Porsche. Who said Porsche here? I'll tell you why. All right, 2 people said Porsche? Okay. All right. Who said Porsche? Gosh, so many people. Can I throw? Okay. Here you go. No, I made my break. I don't want her to drop test on stage. And one more person here. Thank you.
How much pressure can the kickstand or the surface support with the kickstand fully extended?
In terms of,
Some people heavy pressure.
yeah.
They add additional pressure with the kickstand out.
Sure.
Test out the amount of pressure the
Yeah.
kickstand is.
Very good question. One of the things we tested, so we could not get the kickstand into a breakaway position. Like it breaks away and then you can put it back in the same position. So within the launch time frame, so we said, okay, we're going to test with, literally, I'm not joking, we tested with cats. Like, hey, if somebody's cats jumped on it when it was in completely open position, would it break? If a small kid kind of pulls it from the back and it topples, would it break? So those are the tests we did. And between 10 to 15 newtons is what it can withstand before, unless you kind of sit on it on a sofa, usually it shouldn't break. But don't try it.
I already know I'd make it fail.
Porsche is the right answer. So when we were, so one part of the story was over. We made the hinge. We made the assembly right. We used to do a process called passivation. It's an oxidation process where the top layer of the metal is oxidized, and then you kind of paint over it. We learned from Surface 2 that a lot of people had come back and said, hey, there is, when you put a dent, sometimes the paint peels off, or from some of the initial lots, not from all the lots, but some of the customers came back and said, this is the thing. So there was like financial modeling and saying, hey, how many customers? It's only 5% customers. It might be cheaper to give them a free Surface Pro 2, and how do we think about it? So, but we said, we are going to make an investment on this one. We want to make it really absolutely great to use. And then we started looking at, just like Ralph was telling, we kind of look at stuff. We go to a kitchen section in Target, or we go to cars and look at what are the different things that people are doing in other areas that gives similar kind of reliability in terms of performance. So we talked to a company, or we talked to several companies, some of the leading scientists in paint technology, people who have spent like 20, 25 years in the chemical engineering of paint, and said, hey, what we want to do is when somebody hits the device, even if there is a dent, because if somebody drops something, there could be a dent based on thickness, but we don't want the paint to peel off. And what are the places where it happens? So we said, hey, we heard that it was kind of cars are the best places. And then we were talking to this company who were doing the paint process for Porsche cars. So what happens is there is an oxidation layer that happens on the surface, and we use something called a Mag-C process. So that gives you a thicker adhesion between the metal and the, for lack of a better word, primer in between. It's not a paint, but it's an oxidation layer, a primer layer that happens between. And then the paint that you pick has to have great adhesion between the primer layer and the top layer. And cars have kind of perfected that, because usually you dent the car, hit a little bit, nothing happens, it just takes the curve, but the paint doesn't come off. It was super expensive. It was several dollars more than what we had planned. And several dollars multiplied by millions of devices is a lot of money for the company, for the finance team. Everybody looking at it like, are you crazy? Are you building a car? Are you building an electronic device? Cars last for 7 years, and usually computers people buy for 3-4 years. What are you trying to do? Why do you want to paint cars? So we have all this conversation. But as a team, we said, we're going to make this bet. We will figure out how to reduce the cost over time. We will go work with the suppliers, innovate on new things. But we decided to use the Mag-C process in this one. And what you see on this is what's used on Porsche. Yep. Nothing is a stupid question.
So cars are very different
Yeah.
classes, so typically a talent comes from the market now. So the paint's very different. The paints that you use in cars are
Yeah.
very different to something like that where
Oh, sorry. The Mag-C process for adhesion as a primer layer is what's the Porsche process. Yeah. Yes. Yeah. Not on Pro 2. Sorry, surface on a rocket ship? Sorry, I didn't hear you. I'm sorry. Sure. There is always feedback we get. We have stuff on the roadmap. There are a few things I can't talk about, but good feedback. I will take it back to the team so that somebody was interested. So material and finish, we talked about this, and then I talked about the automated assembly process. This is the way we get the extreme tight tolerances in terms of the assembly. How are we doing on time? Can I keep going? I have lots to share, stories to share. Gaps and tolerances, like I mentioned, this is super tight tolerances on each of the components. A lot of times we have to take yield hits on the manufacturing process to keep these tolerances. There is a lot of tension that happens in manufacturing, design, engineering, everybody. But as a team, we always make sure that we are making the best decision for the customer so that when you are spilling something, it doesn't go through the cracks, and make sure it's an absolutely gorgeous product. Yeah?
You were asking about the tight tolerances.
Mm-hmm.
I was curious, did the team evaluate a Kensington block slot? They have one on the docking station, but the problem at work, someone can just undock my surface, walk away with it, but I still have the docking.
Sure. Great point. We did evaluate, but at that point in time, just in terms of the overall priority of things we had to launch, it kind of fell below. But we're constantly thinking about it in other ways. So the thing is, when we put things through the design hopper, we say, what are the things we can do exclusively? And Kensington Lock was one of the things that we said. There are so many third-party manufacturers who are making a living out of that business. Should we depend on them? Should we give that business to them? Maybe they are able to build some. So those are some of the trade-offs we think about when you say, what is the thing that we can exclusively do? What are the things we can get the third-party manufacturers kind of expand the business and build more accessories? So that's the trade-off. So right now, there is a product available in which you have a Kensington lock inside a casing. So when you lock it, you cannot take the device out, and you can lock it down. It's a separate accessory you have to buy. It's not. Hey, Brian Crum is here. Brian, you should answer that question. Brian is our accessories manager. He handles
Hi there,
a
folks.
million
Yeah,
companies.
I'm Brian Crum. I'm on the Surface Accessories team. I'll address this just briefly, but I'd encourage you to come down to the Surface showcase in the expo hall where we have this exact accessory. It's called the Ergotron Locker. It's essentially a dock locker that works with the Surface docking station and actually wraps around the entire device and the dock. So it provides for not only device and dock security, but also secured cable management as well, because we know that's really important. So I'd encourage you to come down and take a look.
Thank you, Brian. Before the next speaker kicks me out, I think we have some time. I'll go a little faster. So we talked about reliability. There is a lot of focus on reliability. How do we make sure that it is kids-friendly, it is safe, when you drop it, it doesn't break? This is a high-speed photography we've done. So we do drop tests, tumble tests, temperature, humidity. When these products are shipped at very low temperatures in a plane thousands of feet away, how does it perform? Does it impact? When you use it in Alaska versus in Florida, how does it happen? So there is a whole bunch of studies that happen. Backpack insertion. We actually simulate conditions where people use the real product and use them, like take 50 or 60 pieces to get statistically significant data to make sure it lasts. It works fine in the way customers would normally use it. This is a quick video. By the way, the drop is from a much higher height. We just take a picture from a lower section with high-speed photography. So we look at, our engineers look at this one image for, I'm not exaggerating, about 2 or 3 hours, just looking at where is this bending and what happens. And then you go and make corrections to this guy. It's like, okay, when it dropped, what happened? And then we drop it for different angles. And study each motion and say, what is the strength characteristic in the material or in the glass that is getting that deflection, and how do we fix it? Is it acceptable? And if not, how do we fix it? So just a quick view of how we do this. All right, How big is the prototyping facility we have in Redmond? Gosh, I have to change the question. This is not to brag at all. There is like team members who've traveled much more than I have. We are all over the place, all the time. Remember that this is one sprint to the other in a period of 9.5 months. God. Who said 126? Who said 126? That's the closest, 132. All right, I think I should give you a good prize. My wife will hate you, but Surface 3? No, no Surface 3. Surface 3 is the most excited person in this room. Gosh, I'm going to get you something else, but for now, I'll give you this. This was a tough one to guess. So once, as I said, we were sitting on the airplane seats and trying out these, but our device is not complete without the keyboard, because that's the story of productivity we are going to say. Originally, if you had seen Surface 2, you might have seen the straight keyboard. We struggled with this for like 2.5 months to figure out how do we make, when you make the keyboard bigger, your surface area becomes larger, which means it can create wobble, stability reduces, and then it goes farther away from your lap, so that it's high likelihood of falling. So one of our engineers came up with this super idea, is that we can make it stronger by having an attach. And then we spent several weeks to get the magnetic force right. As you can see, this attach, we had to put a spec to this attach to make sure it can sit so that it doesn't come off easily. So there is a lot of energy and effort that went into making this right. And then when we did this right, we wanted to make this thinner. And when you make the keyboard thinner, you have to make sure that the travel in this key does not drop to a certain point that people don't like it. And there is a lot of tactile feel that needs to go into it. The sound that you hear. And we spend a lot of sound. Ralph is the hero of that. He spends a lot of time. No. Sorry? No, they're different magnets. They're different magnets. There are front magnets and kickstand magnets separate.
How many magnets are there actually in the circuit?
Gosh, 1, 2, 3, 4, 5, 6, 7, 8. Yep. Oh, that doesn't include the keyboard.
So are you going to go over how you avoided the magnets affecting the actual performance of the unit?
Yes, absolutely. Something I didn't touch on this, there are, as I said, 9 months of stories. RF engineers, they came back and said, hey, your speakers are too close to the RF antennas, and it's going to impact this. You need to move the speakers away. And we said, the only place we can go is out. So we had to do custom routing inside, get the connectors right, do a lot of magic with the motherboard to get it right. Yes, magnets are always something we take care of, both in terms of RF performance and in terms of safety, because magnets can impact devices that you use in day-to-day life. So we have a specification. There is a industry standard specification as well to use what kind of magnets are acceptable to make sure they don't interfere with other things.
Dumb question, does the magnets affect the performance of the batteries any?
No. Wobble, typing experience, keypad, and of course we made the trackpad much larger based on user experience feedback that we got. Yeah. Surface Pen. This is a continued story around productivity. We wanted to make sure that when you pick up the Surface, it's just as good as a notebook. When you have an idea, you don't want to think about booting your device and putting it on, and by the time you put it on, you forget what you're thinking. So we wanted to make sure when you take the device, you can click the button on the pen. It's a whole journey. I'm kind of condensing the story, but you click the button and you can open it and write in OneNote and capture the thought as you're kind of immediately thinking about it. we had a lot of choices. We had choices between electromagnetic, passive pens, active capacitive pens. There is trade-offs. As you can see, we used the Wacom processor, Wacom pens earlier, and then we moved to Entrig. One of the fundamental reasons was, and all these technologies are good for different kind of applications, different scenarios. They're all good. But we wanted to make our latency and accuracy really good. At the same time, we also wanted to add something more than the pen, like open the notebook. So when you press it, you open the notebook. To do that, it requires larger power. And when you need larger power, you have to insert a battery. And then we were saying, if you can insert a battery, then we might as well use it for the front pen as well. And when you use that, you can get better latency and accuracy on the pen. So that's how we kind of did the trade-off, and how do we think about long-term investment in Entrig. And finally, we ended up buying that company last week when the announcement was made. So we are invested in the pen as a productivity device. Sure. All right. You have the answer. So right now, you have to be really smart like him to go figure out how to do it. But in the long term, I'm sure there will be options that we will think about. But that's a part of the roadmap that I usually don't talk about. I only paid to talk about the future. I get fired for talk about the present. I talk about the future, I get fired. Pen, it looks super simple. It feels like, hey, it's like a pencil. What does it take? Input detection is a big deal. What is the input? Is it the finger? Is it the palm? Is it the pen? What are you trying to input? Is it the elbow? There are so many places that you touch the screen with. How do you build algorithms to figure out what is the input? And getting the pen input right is a lot of work to get that right. The second thing is backward compatibility. This is something I talked about, Wacom versus Entrig, and if we change the platform, what happens to our users, and at what point do we kind of say that, okay, this is it, we have to bet on the future. That is something that goes into mind. Screen, the screen thickness. There are several factors on the screen. When people use it, there is oil on the screen, there is dirt on the screen, people put screen protectors. So how do you make sure the chip that you're developing works on all of these without kind of impairing your experience? Angle and stability. So after we did all this work on the hinge and writing experience, we found that in some of the conference tables, when you keep it, this guy goes, this is slippery. So we had to go build a separate foot to make sure the writing experience is great on the device. So that's what you see behind. People use pen in all kinds of locations. So how do we think about that? A few things that the team thinks about. Here's something I want to quickly talk about: software. So Bluetooth pairing, note-taking scenarios I just talked about. These are two things that constantly worry us. What platform do we pick? We talked about that. Parallax. When you write with a pen on paper, you're actually touching the surface. But when you're actually writing with a digital pen on a digital device, what happens is you have the glass layer, you have the touch layer, and then you have the digitizer layer, the pen coils. And then your pen comes here, right? So what happens is your eye expects the dot or the writing point to be here, and the actual writing point is here. So there is a visual parallax and an electronics parallax. And the way to get that smallest is by making the glass thinner. And at a certain point, the thickness, when you make it so thin, it becomes fragile. So there is a trade-off, and there is a lot of algorithmic stuff that our teams do to make sure that parallax is minimized. As you can see in OneNote today, we have really optimized that. The other thing is latency. When you draw a line, how far behind is the dot trailing? How do you get that right? And it is not just the pen. It's the pen technology, the operating system, and the application itself. There is a stack up of delay that happens in the entire thing. The processing is happening as you write, so which means that the delay kind of accumulates and gives you a latency. But in our pen, we have been able to reduce it to really low levels with OneNote tuning. So if you use OneNote, you can see the latency is much lower than some of the other platforms. Sorry? Yes. Ergonomics, that is the thing that I was going to come to, but we'll go to that straight. Yeah. Sure. So we define the specs for that, and we have the manufacturer bonded at source. It's a completely dust-free facility. There are multiple layers that are coming together, and there's a special bonding process. There are TDM engineers or touch display module engineers, like who will be the best people to talk about it. But there is a whole process to that. Yeah. Companies like Samsung and LG and those people have kind of perfected that art. Ergonomics. As I said, our fundamental requirement was making it a great experience for the purpose it is built for. A pen is, the core function of a pen is to write. And we are building it for people who can write, artists who can write for a few hours, so it should not have fatigue when you hold it for a long period of time. So we wanted to make sure that it is really ergonomic. When you make it ergonomic, then your diameter is going to be between 9 millimeters to 10.5. If you see most of the good pens that you see in the market, they are in that size range because it gives you a good grip to write over long periods of time. But then it doesn't help you store well inside the device. For example, some of the Samsung devices have a nice storage inside, as you can see. But our question was, is it a writing device? Do we want to prioritize in writing or storage? Storage is important, but which one should we put the higher order priority? And given the size of the device and how we were trying to make it even now and in future, it was going to become more and more difficult to have a platform decision on how we store it inside. So we said we're going to make the writing experience great, and for a short period of time, we said, okay, we're going to do the loops, but we are constantly, our engineers are right now working on how do we find a different way to store this. So new solutions will keep coming. Colors. It's a completely different ballgame. We have launched color pens. I don't think it is yet out in the market, but this is right here. Who was the person who got sleeves? I'll give you pens. Yeah. So we have blue, black, and red. One of the things we do is when we do the color, there is a whole LAB report in terms of what color pigments we need to use. How do we get it consistent across all the batches of production? We define that. We remove nickel so that there is no non-compliant material inside. But what happens is when you remove nickel from the sealant, when you put it in sunlight, it fades away. So we had to really go invent a new process with one of our suppliers to make it nickel-free, yet pass our UV and reliability test to make sure it can kind of last different places. So it is just insane the amount of energy that we spent last few months on this one. And you have to tell me where you will get a 4A battery. You have to tell me where will you buy a 4A battery.
No problem.
Okay. So here is where our customers are using the pen. Oh.
My name is David William Hearn. I'm a composer. My favorite feature. My name is David William Hearn. I'm a composer, orchestrator, and arranger. My favorite feature of the pen is the fact that it feels and looks like a real pen. And as silly as that sounds, it's really important the way it feels in your hand. Beethoven, Bach, Mozart, you name it, they all work the same way. And now we're writing with a digital pen on digital paper. There's something beautiful about that continuity.
My name is Melissa DiCaprio, and I am a doctorate student. Using the Surface Pen has been a very transformative experience. It's interacting with the computer in a totally different way. I can actually handwrite my notes right directly onto the screen, which helps me remember them better and score higher on my tests. The pen is also great because I can use it in Photoshop and in Illustrator. As opposed to using the mouse and the keyboard, the pen gives me much more control over what I'm doing on the screen.
My name is Seth Yu. I'm an assistant professor at the University of
What is the weight of Surface Pro 3? Wrong. Give me in pounds. Surface 3. Surface 3. God. Sorry. 1.4. You get 2 pence. Because you made yourself heard and you were right. It's 1.4, slightly less than 1.4.
Thank you.
Quickly, Surface Pro 3, you've seen all the announcements, so I won't talk through this in the interest of time. Great device for students, busy parents. It's about 80% processing capacity of i3, but it does all the functions, runs Word, Excel, all the Office software. My daughter uses it for school, and she just loves it. She's able to do almost all the things. So from K to 12 education, it's a great device. And then, of course, we have LTE as well coming soon. This is an interior. It's a fanless design. Because of the power consumption, we were able to optimize. It's absolutely gorgeous inside. And this is a explored view. To summarize, this is all design in Redmond. We don't outsource anything. We are not an ODM model. We design in-house. We build prototypes. We kind of get it to a point where we think that it is ready, and then we go to external manufacturers, find out who has the best capability to build those to the precision levels that we intend. All the stuff, mechanical, electrical, software, design validation, everything is done in-house.
Microsoft is all in on making Surface one of the greatest hardware devices in the world.
This building allows us to design, build, and test, and iterate over and over and over again to reach perfect products.
8 separated labs that are now together under one massive roof.
The fidelity of the problem solving is at a different level.
As a hardware designer, my expectations were blown away.
It's that place where people come together to collaboratively design something. It's a 100,000 square foot building, and we consume the whole thing specifically for our labs.
CNC machines, laser cutting machines, water jet machines, a huge spray booth.
There's polyjet machines. These are all like rapid prototyping devices, down to micron level of accuracy.
Having everything in one place is really incredible.
We'll see somebody working on a model that's totally different than what we're thinking. They can inspire like a new creative way of doing it, and that happens all the time.
We had a meeting where we talked about a bunch of ideas. We're going to have the same meeting tomorrow, and we're going to look at parts on the table. I haven't seen anything like it.
We seek perfection. That's the goal for Surface. Perfect products. And this building allows us to get closer and closer to perfect.
It is a lot of teamwork. I get a chance to talk to you, but there are so many people who are working behind the scenes to make it possible because we love you. We love the work that you do. We want to make sure it's a great product for you. If there is good feedback, tell us. We love it. If it's bad feedback, we love it because it helps us improve our products. So keep the feedback flowing. Thank you.